Day 3, Problem 1. A 20-foot ladder is leaning against a tower. Its base is 6 feet from the tower. Part A, sketch a diagram. So we need to have a tower. For that, maybe just a rectangle shape. And here's the ground. And then a ladder leaning diagonally against the tower might look something like this. Now, we recognize this in math class as a right triangle, where there is a 90-degree angle where the tower meets the ground, and we can label this with some measurements given to us. The ladder itself is 20 feet, so it's this side of the triangle that gets labeled 20 feet. And the base is 6 feet, so across the bottom, this is 6 feet. And that is a diagram for Part A. Now, Part B, use the Pythagorean theorem to find how high the ladder reaches. The Pythagorean theorem is a squared plus b squared equals c squared. And these three letters represent the three sides of any right triangle. The letter A is the shortest leg of the right triangle. In our drawing, that appears to be this side here that has 6 feet on it. So fill in 6 for the letter A. The letter B is the next longest leg of the triangle, and that is this side here. That's the one we do not know, and so let's put a variable on it, the letter B. And then the letter C, that is the hypotenuse of the right triangle. In our drawing, that is the ladder that has 20 feet written on it. So the letter C gets replaced with 20. So here's an equation that we'd like to solve for the variable B. Now, the 6 squared is being added to the B term, and we can remove the 6 squared using subtraction. So subtract 6 squared, and on the right side of the equation, subtract 6 squared. 6 squared subtract 6 squared makes a 0 in this position. And then the b squared can be brought straight down, and that is equal to. Now over here, 20 squared subtract 6 squared. Let's figure out what that is. 20 squared is 400, and subtract 6 squared is 36. So we'd like to figure out what 400 subtract 36 is. Okay. We can borrow from 40, leaving 39, and the 1 that we borrowed, bring that over here to create 10. 10 subtract 6 is 4. 9 subtract 3 is 6. And then 3 gets brought down, 364. So we have b squared is equal to 364. To solve for b, we need to remove this exponent, and we can do that using square root. So the square root of b squared is equal to the square root of the 364. The square root of b squared is b, and that is equal to, now the square root of 364. There might be a whole number that multiplies by itself to make 364, or perhaps we're going to have to take a decimal guess on that. And so let's figure out what the square root of 364 is. Let's try 18 times 18 and see how close to 364 that is. So on some scrap paper, 8 times 8 is 64. Write the 4 and carry the 6. 1 times 8 is 8, plus 6 is 14. And start the next row with 0. 1 times 8 is 8, and 1 times 1 is 1. Add these rows together, that's 4. 4 and 8 is 12, carry the 1, and 1 and 1 is 3. That's 324. that's not large enough to be 364. So the square root of 364 is more than 18. Is it 19? Let's find out what 19 times 19 is. 9 times 9 is 81. Write the 1 and carry the 8. 1 times 9 is 9, plus 8 is 17. And start the next row with 0. 1 times 9 is 9, and 1 times 1 is 1. And then add these together. That's 1. 7 and 9 is 16. Carry the 1, and 1 and 1 is 3. So 19 to the second power is 361. That is very close to 364. It's still not quite big enough, and so our answer for the square root of 364 is going to be a little more than 19. It's going to be 19 point and then some digit that we can guess for our tens position. Now, because 364 is so close to 361, I'm going to guess maybe just the digit 1 for my tens position. And so I think that the square root of 364 is approximately 19.1. And so in our original drawing, the variable b, which is this side of the triangle and represents how high up the wall the top of the ladder touches, is 19.1 feet. Now, day 3, problem 2. Part A, graph figure ABC with vertices at these 3 spots. So let's take care of that first. Point A is at 3, 0. So here's the origin, and 3, 0 is this position here. That is point A. Point B is 3, 3. So here's the origin, and then 3, 3 would be over 3 and up 3, and here's the dot. This is point B. And point C is 1, 4. So here's the origin, over to 1, and then up to the 4, and here's the dot, point C. We can connect these together to create a triangle. Okay. And so that takes care of part A. Now part B, graph its dilation, A prime, B prime, C prime, if the scale factor is 1.5. What a dilation is another triangle that is the same shape as this original triangle, but its size will be different. And we're going to find this triangle by using these letters that were given to begin with and multiplying them by the scale factor of 1.5. So let's start with point A. Point A is at 3, 0. Now its dilation image, which we're going to call A prime, can be found by multiplying these coordinates by the scale factor 1.5. So let's multiply by 1.5 and see what we get. We're going to call this A prime, and its coordinates will be, let's see, 3 times 1.5 is 4.5, and 0 times 1.5 is 0. So point A prime is located at 4.5, 0. We can find that. Here's the origin. 4.5, 0 is to the right. Here's 4. Here is 5. 4.5 will be exactly in the middle between 4 and 5. So right here is the dot, and this is A prime. Okay. Now let's work with B. So point B originally is 3, 3. And we're going to find its dilation image by multiplying by the scale factor of 1.5. That is going to create a dot called B prime. 3 times 1.5 is 4.5. And for the y-coordinate, 3 times 1.5 is 4.5. Let's find point B prime. Here's the origin over to 4.5 and then up to 4.5. And this dot is B prime. Okay. Now let's work with point C. Point C is originally located at 1, 4. Let's multiply by the scale factor of 1.5 to create point C prime. 1 times 1.5 is 1.5, and 4 times 1.5 is 6. And so we need to find 1.5, 6. Here's the origin. Here is 1, and then halfway to the next mark is 1.5, and now up to the 6. That's here. This is C prime. And then we can connect those 3 dots together to create our new triangle. Notice that the red triangle is similar in shape to the original triangle, but it is larger. And in fact, each side of the triangle is 1.5 times larger than the corresponding side of the original triangle. For example, here's the original triangle, one of its sides, and then the corresponding side in the image is 1.5 times longer than that side. That is the drawing, which takes care of part B. And part C, which says find the coordinates of the dilated image, we have actually done already, because that's how we were able to draw that dilated image to begin with. So part C is finished already.